it's a little tricky via this hardware. So the like you saw previously, it is not the same kind of environment everywhere. So on the login node, on the GPU node are not the same kind of environment. So you need to be careful. So you need to compile. I will do it, but I have in the README. So please check the README inside the ATPESC 2021. This is a GitHub. So you can log in. You can git clone only on the Theta login node. On the Theta SN login node, you cannot access the internet. So please, I say here on the non-GPU login node, just on login, just git clone the example. Then on the GPU login node, we'll compile the code, right? And on the Theta compute node, we'll run the code. Okay, so we'll do what good HPC people are doing. They are compiling on the on the login node and running on the compute node. So also because the path, the file system is a little strange, it's not the same module file bit inside the compute node and the login node. So one should be careful. So, but just follow the README and everything should be fine. And this is what I will do right now. And I have multiple examples, so we can follow with example. And if you don't want to follow my example, and if you just want to do some exercise, or if you have an idea for a SYCL project, what I can suggest you is, in HPC, we are only interested by two things, right, from the hardware. There are just the number of flops they can do, so the number of FFMA, and the bandwidth they can achieve. So I think a nice project to start in a programming language is to be able to write a kernel who is able to reach peak performance and to reach memory bandwidth. And if you can do one kernel, we can do that at the same time. It is perfect. And it should not be too hard to start working on that. And after, if you have any question, you can do that. So, but if not, just please with me, follow my example. So they are just like nice introduction example to really build up the knowledge one step by step. So we'll go from really simple program to really more advanced stuff with STD placeholder and DAG and all this kind of good things. So just tell me if it is too fast, too slow, because it's really more for you that I'm doing that, right? I wrote the example, so I know them. So please tell me what you want to know, what kind of example. For example, somebody asked a question about a functor. So I will show you an example of a functor. So let's go this one. So I will compile the first example. So I will have this terminal here to be able to compile and this terminal here to be able to run. And I suggest you to do the same. Okay, so let's load all those module files on the GPU FN. So I will go in 9 SYCL of hell, where I have 9 example. Okay, in mine I have more things. I work on it. It will be clean. So I load everything. So I have DPC++, like we say before, it's not really DPC++, right? It's Clang. So if you do let me put in full screen, sorry. So I load those module files and I load DPC++ and HPC. And if you do which Clang++, it should be this one, the DPC++ Clang++. Compiler. So just to compile, so because it is maybe, how can I say? It depends, so you have a lot of different options and everything to do. So the first thing is to make, for example, let's do the tiny SYCL info, right? So if you just do make 0 tiny.info. So the compile option, so nothing fancy. You use Clang++ because it is a compiler. You compile with st.17. It is now the version of C++ that is required by the SYCL specification. You pass fSYCL, you pass fSYCL target NVPTX64 NVIDIA CUDA SYCL device. This one is just to say that when you compile, you want to generate a fat binary, will contain some PTX we needed from this, some PTX. I think it will be general, not optimized for SM, but I don't know. doesn't matter. And after here, a no conversion is just to silence some version number that CUDA can have. So you can make it, and on the other side, on my other nice terminal, I just need to load the correct module files to be able to get my correct setup. I think I just need a libcycle. This is the only thing I need. So modules use soft module file module DPC++. And now I have access to this libcycle.so. And if I do 0 tiny cycle .info, I have that data. So this work, and now I just want to go through the code, this first example, because I think it's nice, right? In you have a NVIDIA SMI. I think this is right. It exists, SMI. No, okay, I cannot. I don't remember the name of the NVIDIA command to be able to list the GPU and to leave the GPU properties. And we just want to do the same, right? I explained to you, you have platform, device, and this code, we try to do exactly the same. So let's try to do that. Continue some info. And it is nice because it is something always when you go in the system, you want to see how many GPU I have per node, if there are CPU, GPUs, what can you see? And here it is the first example. We try to do that. And this one is more or less to show you that SYCL is really well integrated with C++. So nothing especially fancy. You see here, I try, it is a free function we don't live anywhere. It's a free function I call get platform. I will have it return me a std vector of platform. I use a for loop. Now I want to use get info. So get info will be able to get some information from this platform. You see here, because it is C++, it's not in C, you will have done plat get info and after pass, I don't know, some enum or something like that. Here you specialize via a type. And so you do SYCL platform name, for example, SYCL place for vendor, SYCL perfectio platform. And everybody, the platform and the device have this get info that you just need to template with the correct type. So you can just read the specification to be able to get that. If you have some C++ guru here, I would be interested to see how can you create a list of type and iterate over a list of type. I tried to do that. I was not lucky, but I'm sure somebody in the audience.
That'd be a whole nother talk.
You always have one guy who's super good at C++. So if you want to do that, you can send me. Yes, so still have the issue. Yeah, so no problem. So I can just when we do finish this one, I finish this example, and after we can redo together from scratch, maybe a compilation just to see. And you can follow me and I can ask everybody if they can follow me. So you get a platform, and after now for each platform, you can get devices and you get a vector of devices. And after you can use this auto loop, and after you can ask the name and if it is the GPUs. Exactly with a little ternary to be able to run. And so if I run that here on my other terminal, not this one, I have too many terminals. Sorry, this one. Here, if I do 0 tinycl.cl info, you see, I hate when they do that. I see here, because I am on the queue with only one GPU, I see I have only one GPU. I have two platforms, and one platform is this NVIDIA CUDA backend, NVIDIA Corporation CUDA. It's a long name. And after in this platform, I only one device. If you are not in the single GPU queues, you will have multiple devices. In my case, I was nice. I use a single GPU to not take over too much resources, so only one GPUs. Another platform, the SYCL specification require or highly encourage people to have a host platform with kind of a platform with always here to be able to debug your program. So it will run on the CPU or something like that, right? And it is just a convenience thing. So let's retry one more time the compilation step. So first, you need to be on Theta GPU SN2. I never try on any other things than Theta GPU SN2. Abby, did you try on Theta GPU SN1?
Oh, yeah. Yeah, I did.
Okay, so maybe it works on Theta
N1
GPU.
or N2.
Yeah. Okay, so you should be able to use that. Then what I suggest you is to cat in a presentation, 2021 aspect at ATPESC, the README, and in the README it will give you the module to use. So I suggest you to be able to either copy paste for them or just do it one by one. So if you do that, you'll be able to compile NVHPC. Did that work until there, Ryan?
It doesn't seem to be. I'll paste a screenshot in the chat or in the Slack.
Yes, to state. I mean, 80% of the job of APC people is just to compile their code, right? It is part of the fun. Oh yeah. Yeah. So make. Yeah, it's because you didn't define. So perfect. So it's good. So let's continue. So you see here when I do make, I need to specify the CXX because by default, maybe it's a limitation of our module file. We don't define our CXX compiler by default is not Clang, it is NVC++. So you see in your code that you show the compiler is not Clang++, it's NVC++. And of course, NVC++ have no idea how to compile or to link with the SYCL. It doesn't know the option. So the only thing you need to do is just to export CXX equal Clang++, or just do this thing where you define CXX and CXX flag inside the make. And this should save all your issue. And you should do make all -k because I think by default, my make file tried to compile and run everything. And it didn't. It will not work on this configuration where we are on the compute node. When we are on the login node and not the compute node. So in theory, just do CXX Clang and CXX flags and make 0. So if I redo that, so I copy paste CXX flag, all this kind of crazy option who are correct in your case, and after just 0, 0 TNCL, I don't remember. Make this guy minus the CPP, and can remove it. And you are sure it is C++ because it takes 20 minutes to compile a 2-line program. So that means they are doing something really optimal. So we are good.
Thomas, you might get better compile performance on a compute node. Adam is suggesting that.
No, I cannot. It's not the correct environment, and some library are not here, not the same version.
Oh,
the
okay.
Compiler.
Okay.
It's just not possible. Don't.
Okay, if that's the case, then I take back the advice that I relayed.
Yeah, I tried to do that before, but sadly, it's not possible. So it's. So we have tiny SYCL info. So if you want, we can just, you can change some information. If you don't want device name, you have, for example, the number of compute unit, and you can change here the number of compute unit, right? So either open the specification document or find some other example online and everything. So it can be useful to do that. Let's go for your first kernel that you wrote. And this one is maybe, how can I say, too much verbose because we try to print. And maybe you never realize, but printing is super hard on GPU because printing means you need to allocate an internal buffer. First, writing stuff in this internal buffer, at the end of the program, flush it, or maybe via this kind of streaming, flush it, so it's complicated. So printf is complicated. Some people say you have an error on no init, and yes, it is expected. Yeah, it is my bug. It's because no init without the underscore is part of the SYCL 2020 standard, who is not yet implemented in our compiler because maybe it's a little old or something like that, or maybe not really merged. So you should just replace, for once, just follow the compiler advice and replace no init, no underscore init with just no init, and it should work. So sorry, on my Intel machine, it was working. I didn't, I modified one of them, but not two of them. So sorry about that. So here you see we create a queue with the GPU selector. I print this one. I think it's always nice to print, from the queue, I got the device with associated to that, and I print the device name. So you can always be sure when you are running that you are running on the CPU, on the GPU or something like that. So this is always a little logging is always welcome. And after here is just to introduce you to a single task. And a single task, they are not parallel for. They are just thing will execute only once. It can be useful from some particular cases, and it is really useful just to show you step by step the construction of a program, right? Because here it is really minimum. I have nothing, no buffer, no nothing. It's just a queue that I submit. I have this command group handler where in the future we'll be able to create buffer, accessor, and everything. And here I just create a stream. I need to say the size of the stream because I told you print need to allocate some memory. So this one is more or less the memory they allocate. And after you create a single task and you compile, and you see here, I do q.wait. If you don't do q.wait, you may have some horrible error message because the kernel may finish. I mean, your program may stop executing, starting freeing a lot of stuff, but your kernel didn't finish. So important to wait here. So same, so on theta GPUs and do, I take exactly the same big CXX. I should have export, but at least this one, no, it is verbose. And I can do my first kernel.cpp. It compile. And after on the theta GPUs, the compute node, I will be able to do my first kernel and it print hello world with the name of the machine. So nothing fancy. And now I think we'll go on the ND range. I don't think we need the parallel for. We can go later if you want. So the ND range is maybe more interesting because it will show you the introspection capabilities of SYCL. So at the beginning is nothing, just parsing. I will pass as an argument of the program the global size and the local size. If you remember the slide on GPU, you have a global ID who will be after partition in something called a local workgroup, and this is the size of the local workgroup, local range and global range, as SYCL do. So at the beginning, nothing changed, absolutely nothing. I will still do print. If the device we are running is a regular CPU, any override of using SYCL rather than just writing the code directly? I'm pretty sure yes, because it will be an override, right? I don't think the compiler is magic enough to just transform everything as no ops, but I'm not sure, honestly, then it will be, I never measure, to be honest, so I don't know. So yes, it will be an override. I expect the override to be really slow, really small, but I have no idea how much it is. It's like, I have no idea. I expect like OpenMP. If you put, yeah, I expect just like OpenMP. It's the same override on CPUs. But please measure. It's always the answer, right? In our domain, please measure and benchmark and see. So here, it is a question of the introspection capabilities on this kind of ND range. If you remember this picture, I have a lot of data. I want to know, where is my global ID? My local ID, if you are come from MPI, it's the world rank size, right? Where you are on this big list. Work size is really like where I am on this already number of group, local ramp, local size. So you have all these data that you need to be able to do some introspection on your algorithm. And you see here, like I told before on CUDA, most of the time, you don't have an index. So if you port your code for CUDA, what I hear a lot of the time is like your infrastructure never ever has this context of passing an additional argument to your functor to be able to get this get global ID. They are not free function. You need to pass an index. I find it more elegant to pass an index, but I understand that if you come from CUDA or OpenCL and you didn't design your code like this, it's painful. But yeah, this is the way it is. So you need to have an additional argument of all your functor or CUDA function when you port 2c to be able to pass this index. And here I will print everything. So world rank, world size. So the total number of, and after local rank, local size. So in which the vectorization length, one can say, or what is my index inside the team. And here, what is my team number, right? So nothing really fancy. It's like the introspection capabilities if you want to design your algorithm. And when you develop your code like this, what you do to gain performance, if you start to auto-tune this local range, like Christian says, this local range cannot take arbitrary values. You can query the hardware for some of the values. Different hardware will have different best local range, different compiler even, because the local range can impact the size of your kernel, your register pressure and everything. So you can try to be really, really smart, understand your hardware really, really well and hardcode it. My advice is just to auto-tune before you run really large production run, is to have an auto-tune capabilities inside your application where you can just loop over a range, sweep over a range of values and take which one is better. Okay, let's try to compile and after we can run and play with it and see the different data. Yep. Perfect. So 3 ND range, I run. So by default, I think I use 0, 0. So let's say I want to run 12 kernel in the local group size of 6. Maybe it's too much, or it's okay. So you see my this one, first you need to, Christian say, all work items are not executing in order, right? I have first the work item 6 with executed, and after the work item 0, and after the work item 7, and after the work item 1. So it's totally random because this is the way it is. On the local rank size, you see here, it is, I have the first rank size, the first group of data we're executing, and after the second one, and after the 0 EM, a guy who is executing, and both of them are executing the first work item, right? You see, this is what you saw here. And after they do that again for 0, 0, 1, 1, 2, 3, 3, 4, 4, 4, 5, 5. So this is how it works. You see, it's 0, 6 after 7, 1, and after 8, 2, 2, 9, 3, 10. Maybe something really important to consider on GPU is like you have no control whatsoever in the order of execution. You cannot do threads are executing in any order. You just have some possibility of synchronization between a few of them, who's the one who are inside, who are sharing the same group size. For example, this thread and this thread, they are both in the group rank 0, so they are able to synchronize if they want. You can put a local barrier. But this is all. You cannot synchronize between this thread and this thread, for example. So hierarchical parallelism may allow you to exploit that more, but your algorithm need to handle this kind of case, right? You need to be able, you have this restriction where you can only sync on the second layer of parallelism, no, never on the first. So it may be the more advanced stuff. Okay, so now maybe we can do, let's see, the copy device to host, I think will be interesting for people. Yes, because it will show you multiple things. It will show you first the buffer, like I show you, and maybe also, because buffers are nice, but sometimes you want to access the data on the CPU, right? You do some data on the GPUs, and sometimes you just want to be able to check, right? To do some logging or to do some debugging, and you want to have something. And how you do that, right? Because you create an accessor, you need to create a queue on the CPU, or how it's worked to be able to bring back the data on the CPU without destroying the buffer. And this is what this example will try to do. So here, the first thing is I create a vector. I create a buffer, like I told you. I create a queue outside of everything. And first, so you see, I don't create a scope. So I will need to be a queue weight and all this kind of magic. I create a queue, I create an accessor with no init. We need to change it right now. Oh, no init. And I initialize this data. And now, how can I know? I want to update A, right? What I want to do is to be able to update A, because for logging perspective or something like that. I want to do that, but I don't have buffer, I don't have accessor. How can I do that? And the question is to use update host function. And the update host function will take, you create an accessor of your buffer and you run it. And what it will do, it will synchronize the buffer and the data where the buffer was creating to. So it will update this buffer and the value of A, right? Because if not, this will happen only on the destruction of the buffer. And here I won't do it before the destruction of the buffer. So I update host, we mean, really what does it mean? Please update what is the host pointer of all this buffer with the current value of the accessor of the buffer. And after I just wait, if I don't wait, when I will try to access 8, I will have garbage values. So this is the code. So creating a buffer, modifying the buffer via accessor, and here updating the buffer or synchronizing the buffer with the original pointer who was used to create this buffer. And this pattern is really convenient to when you want to debug or something like that. In theory, you want to keep the data as much as possible in the GPUs, but sometimes it's good to be able to just to log and something like that. And the good thing here is like if one day you don't need to get back this data, right? You are in non-debug mode, you can just comment this thing out and it will optimize all the data transfer for you and stop doing this GPU to CPU. So this is important. I think it's a nice example. So let's try to see if it's work and maybe we can play with it and see what happens if we break it. So make 5 copy to host. Perfect. Okay, we can put G, for example, 100. And you see in the G, it's good. And maybe what can we do is let's see if I remove this queue.wait. And in theory, And this is a problem. Bad thing may or may not happen, right? Because I will try to access the data who have not been modified, but it depends on the runtime. So the runtime will not impose any synchronization. If I am lucky, the kernel already finished and I'm good. If I am not lucky, I'm doomed. So let's see. Let's take the bet. So it's worked. So it seemed to work. So in this case, I've got pretty lucky. And maybe if I could super large, no. So I got lucky. So that means this queue finish before I have here. Oh, so I got pretty lucky. And now let's do something totally wrong. And this one will never work for sure. If I do that, of course, the data will be incorrect. So let's see. Oh, maybe I didn't recompile. No, I think I recompile. And you see here, my buffer is equal to 0 because it is equal to 0 because I didn't call my buffer destructor. And because I didn't call my buffer destructor, I don't have this update host, implicit update host who happened. So that means it didn't work. So it is really as expected. So we have a question. No, if you 2 parallel 4, what's the integer from 1 to n to the GPUs? Okay, so let's see. So here the question is, you don't want to, oh, it is a reduction because you have a reduction, no? 2b parallel 4, maybe it's in advance, I don't remember how it is. Advance Inferno? No, I don't remember. Do you? 2b parallel 4. Do you know where it is?
It's just 2 parallel 4.
Oh, it's 2 parallel 4?
Yeah, I believe that is.
Okay. Okay, so the problem of reduction. So reduction is a tricky business, I think. So we have a question of reduction. I will show you. I think I have a reduction example. And now you need to be nice with me because, of course, I didn't try those examples on this hardware and this compiler. So I'm pretty sure I have a reduction example somewhere. Let's just find it. I think I put it in bleeding edge, reduction.cpp. So I have a reduction. So reduction are tricky, right? Because when you do a reduction, at some point you need to have synchronization, right? Because a reduction means that you need to accumulate something. And when you accumulate something, you need to have some kind of synchronization, atomic and everything. So if you do just a result plus equal something without saying to the compiler it is reduction, you will have a race condition because all the thread will try to route on this value. Right here, I have an accessor and I do plus equal. If I didn't say to the compiler that be careful, this kernel is a reduction kernel, each thread will try to access accessor, but I will not put any reduction, any atomic or something like that, right? So it will have a race condition. It is similar that if I wrote that in OpenMP, so for in E equal whatever in n E plus plus. And here I do A plus equal 1, right? And here I do pragma OMP parallel 4. This one is a race condition because each thread will try to access this one. So at the end, I don't know what I have, but I have wrong result. So either I can do atomic, pragma atomic. In this case, it will work, but it will be slow because each guy will do an atomic, or I can do pragma reduction A0. And if I do this one, it should be faster because I give more flexibility to the runtime to optimize the reduction. So most of the runtime will do kind of a tree reduction, or at least inside the team, we do like a warp reduction or something like that. And just at the end of the tree, they will do some atomic, or some implementation are atomic 3, whatever. The way of doing it is indeed you need to do a reduction. And like we show with Cocos have a parallel reduction. In SYCL is not really the same thing. You have a parallel 4, same thing. You pass an end-run, same thing. It's just after the end-run, you pass this single 1 API reduction because it is Intel who put the reduction into the standard. So they are implementing inside their own namespace, but no, it is standardized. So it will be just SYCL reduction at some point. It's just right now it is not, but it will be. And after you say the accessor you will use to do this reduction, right? Which variable you will use to do this reduction. And after, what is the reduction operator that runtime need to use? In OpenMP, it's the same thing. If you do a min reduction, you need to put OpenMP reduction min. And after here, you got your get global ID of your kernel, right? And after you use your accessor, and you will be able to use your accessor S. And here my accessor, my buffer are inside the scope, so I will be able to use it. So now I am stressed. Let's see if this code compiled here. I'm pretty sure it will not, but let's see. This is the beauty of live demo, because I didn't compile for a long time. Oh, yes, it didn't work. So let's see. There are no matching constructor for enable if stdiff plus. Oh yeah, I think it is will not think live. I think I cannot use std plus. I think this one was implemented only in the new recently. I think now it is std1 API plus something like that.
Oh yeah.
I don't know.
It's supposed to be the same. They will eventually be the same.
Yeah, exactly. It will be eventually the same, but I think right now it is not. At least it is in our newer compiler. I think this compiler is a little little thing. Can try, but I don't. Yeah. So please check up-to-date documentation on how to do that. But it is
the only reason it can't use the standard one, it has to know what the type is, because the plus equals shortcut for combine.
Oh, you mean
that's the only reason it cares, right?
Yeah.
It says if I know this is plus, then I can use plus equals to do combine.
Exactly. Yeah. So sorry, it's always sad when you have a code. So I will make it work, and I will let you know after when it works. I can update it. So I maintain this Git repo most of the time, but now we have divergence between the compiler implementation. So sadly, it is the case. But yeah, so you have reduction in SYCL, fortunately, and you have. Like Christian say, you have reduction in the parallel 4, but in the hierarchical parallel too. So if you create another parallel 4 inside, you will have also a reduction, and inside the subgroup with this kind of fancy thing. I see something who is important are event.cpp. So it is this question of tag, right? So you can use, if you create buffer, it will create tags automatically for you, buffer and accessor. So you don't need to care. But maybe you have you use USM, and if you use USM explicit with the malloc, the runtime have no idea if you have dependency or not, right? Because of aliasing rules, maybe you have, maybe you have not. So one way of doing that is like to do like OpenCL or any other task-based approach. You can use event to be able to synchronize. And this is what I will show you here. So I don't know why it is SYCL event. Whatever, I think it should be SYCL. I will not change live demo, but so each queue submission, every time you submit something to a queue, it gives you back an event. This event can be used for a lot of things. we show in the example, this event can be directly used to do .wait. So you can just directly wait for this event. This event can be used for profiling. After when this event, you can say, please, you can ask the runtime how many nanoseconds it took for this kernel to run. So events are really powerful. And most importantly, maybe events are used for doing DAG. So here I create an event 0. I create an event 1, and I want to be sure when I run event 1, I want to be sure that event 0 is finished. But I'm not a guy living in the cave and doing programming like the 70s. I don't want to put big barrier. I want to be fancy and to create a dependency graph. So the runtime will be able to schedule everything for me like really nice. So to do that, I use event. And when you sub in your kernel, you say, be careful. This commands group that I use will depend on the event 0. And this guy take a vector, I think, of event 2. So you can say, I will wait on all these different events. And it is really useful to do that because you are building something really robust. I mean, really, you give the maximum concurrency. You tell to the runtime the maximum concurrency. Where you do queue wait is really like the big hammer where you say synchronize. Here you do really the lower grain synchronization, fine grain synchronization. So it gives you a lot of information. And so I run this kernel, and after I have another E1, and now I want to use E1 to be able to get some information of my profiling data. And so this is how you do E1 get profiling info. And after you can ask also E0 get profiling info. And I want to know what is the time I took before the command start from E0 and the profiling start with E1. And I print that both kernel on the GPU took this kind of thing. So they are pretty nice. You can really build a lot of, I think this is the best way of expressing any concurrency you have on your program, because you are really able to fully utilize all the concurrency of a GPU like this. We talk a lot about the concurrency between inside the kernel. So it's really important to exploit the maximum concurrency inside the kernel, but also in a lot of apps, you have a lot of kernel who can be executed at the same time. And by using event, you are able to create this tag of dependency. And I think this is really the key to get a good performance code will scale on current machine and future machine. And the event are waiting. So this is nice. You don't need to do a E1.wait. It makes sense that if you want to have the profiling information, you need the kernel to wait. So E1 and E0, any profiling information will wait. Something maybe I forgot to say is here, if you want to get a queue who do profiling, you need to pass an argument, because some hardware have some restriction on how they can schedule stuff if you need profiling information. So this is why you need to say that. And I lost my node. Let me take it back. So do we have any question? Does enable profiling indoor performance? I know it was true, at least before, that when you enable profiling, you destroy concurrent execution. Because if you ask for profiling, the runtime needs to understand when the code was submitted and when it stopped. And if you have concurrent execution of kernel, it may be harder. So some implementation decide to really destroy any concurrency. So you cannot, when you use profiling inside the queue, you cannot have two kernel executing at the same time. This was true. This was fixed in the implementation I am thinking of, but it may be able to, you may be able to check. So the check is easy. You just issue 2 kernel, would take forever, but don't use the full GPUs. So you put a for loop with a bunch of FMA, and you time your code without profiling and with profiling, and the time should be the same. No problem. How does the DAG get scheduled on the device to achieve maximal utilization? So it really depends of the runtime. So here when you're in CUDA, so I think in CUDA you have, Habi, correct me if I'm wrong, you have something like launch graph or something like that, right? Something like this exists, I think. I remember reading the API some point. So how it does is like, wait, please go ahead.
Are you talking about the CUDA graph?
Yeah, you have CUDA graph, right? It is something who exists.
Yes. Mm-hmm.
So in theory, a really smart implementation can take this code at runtime, create a CUDA graph, and submit the CUDA graph. It should be able, and then you rely on CUDA to be able to fully optimize the maximum utilization. So the scheduling is not really, this is what is nice, I think, in my opinion, on this kind of API-based approach is SYCL is the only job of SYCL or in Cocos or in OpenMP, whatever, is to issue the correct command, low-level command to CUDA or to OpenCL. And then we rely on CUDA to be able to schedule it efficiently. So it's really a separation of concern. I think it's a nice, it's always better. So like when everybody have a little responsibility and have less job and need to do it well. I hope this answers your question. Thank you. And one way of checking that, and I encourage everybody, one of the rules of HPC, it doesn't trust anybody, always measure and always profile, always trace. NV, Prof, or other tool is allow you to see which code are executed in CUDA, which code are executing in OpenCL or in level 0. So I encourage you to try to understand that, to spend a little try to understand CUDA on OpenCL and to be able to see if it really is doing what you want, right? In this case, I really expect CUDA to not do any CUDA synchronize, right? It's not because I put a tip on that I should not see a CUDA synchronize. If I run this code, I profile this code, I trace this code, I see a CUDA synchronize, I will open a bug issue to the runtime people, to the SYCL compiler people to say they should not do that. It is not performant. So yes, I think it should be important to doesn't trust anybody. And the good thing is it's pretty trivial. In CPU land is more tricky. In OpenMP doing what they are doing, in CPU it's harder. On GPU, because we are all using this kind of low-level API, it's kind of easy to be able to see what the low-level API are doing in simple cases and report any bug, performance bug. Let me try to recursive. Oh no, I already did it and I got it. Nice, good. Okay, so we saw everything here. Oh, maybe something who is important for the C++ people is the allocator USM that I moved. Oh, let's go from 7 buffer USM.cpp. Yes, exactly. So, you have first 0 and after 1. This is wrong, indeed, in the print. So maybe the problem is it's the print. So let's see. Let me run 8 event. Oh, depend on E0. So indeed, the print is really wrong so let me try. Module use module load DPC++. So if the people who don't follow the Slack, Steven tried to run 8 event, and we see here on the print, I should first print hello world 0 and then hello world 1. And when you run it, you have first hello world 1 and after hello world 0. So I want to see if I can reproduce. And if I can reproduce, I think it is a problem of flushing of flushing the printf. It is my guess. Let's see. So I compile here. I have it. Because I have I have more complex example of DAG after. Okay. So I have always 0, 1 in my system. And okay, so I cannot reproduce this 1, 0. So, oh, us dependent. Oh yeah, it's because you try to run on the SN node. And this one, I have no idea. So you run on the host. Okay, so it looked like maybe the implementation of the CPUs on the, to be honest, I didn't try that much on the CPU. So it looked like the CPU backend doesn't handle well the printf, right? You look at the printf, it doesn't work. Because it looked like on the GPU is working and on the CPU is not working. And so here, not do that slide because maybe not the most interesting, but I think it's important I will try to investigate more. So first thing is on the CPU, I have no idea if you are using, I guess it is purely CPU's stuff. So it doesn't use, for example, the OpenCL backend to run on the CPU on θSN. So maybe one of the issue is maybe a straight bug on their implementation on the CPU. I think the implementation of CPU is far less tested. So maybe it's because of that. So one thing one can do to be able to understand if it is a printf issue or if it is not a printf issue is to really create a dependencies. And I have an example, I can show you that. And not printing, right? Try to see if you have a race condition on AI and AB. Because like I say, printing is tricky. You may have flush issue and this kind of thing. Maybe it's not.
I think it's a bug because Endel's supposed to flush.
Yeah, but honestly, I saw so many bugs with print, but yeah, I guess it is a bug. It looked like a bug indeed. I think you see, you report your first bug. You just need to know to open it to Intel LLVM GitHub and your contribution to SYCL will be amazing. So it's also because we are on named, so I don't know. I think it's SYCL on CPU is far less tested indeed. Yeah, so I think it's because, so you see running on the host is here. I create a queue. I think maybe in my first kernel, I was specific saying that I want a device, a GPU device. And here the error you saw is like device not found because indeed on NVIDIA SM, you don't have any GPU device. So this is the error that you expect that, sorry, I didn't find any device. If you change the queue selector to not ask for a specific GPU, but just say, please give me a device, you will get this host device. And I think this is what we think. So because you will run on SYCL host. And I think SYCL host, yeah, Intel got a little, how can I say, difficult story with him. It looked like a complicated relationship between SYCL host.
Yeah,
and
it's low priority because SYCL is really designed for devices.
Exactly. And I think if you use OpenCL and targeting a CPU backend, it will be better. But yeah, so I think this is why all these bugs on CPU are maybe low priority, but it's still a bug and we should report it. And yeah, maybe I never talk, and maybe it's a good, the error message that you can do that if you go on error handling. Because like you see, you can have error, and you can use a traditional try catch to be able to catch error. So you can say, please give me a GPU, and you try catch that. And if you have an exception, you can say, I didn't find any GPUs. This is what happened in the example of Milo, where if you are not on a compute node and you ask for a GPU, you will just say, I didn't find GPUs. And in application, real world application, you should put try catch everywhere. Yeah, Nevin, did you say something?
No.
No, perfect.
It should be exit 1, but other than that.
Yeah, exactly. Yeah.
Yeah, just in general in CPU programming, you should. I mean, I wrap all my mains with just something that'll catch, like, you know, the last line of defense to say, here's the exception I got. Goodbye.
Yeah, exactly. I think it's a good idea because it's always work, right? And the day you change hardware, you start to have like really strange exception because you never think about this kind of thing. So it's always a good idea to do try catch. So you do that in your library. So now we have 45 more minutes, 40 minutes. So either we can have an open chat if you have any question more about anything related to GPU programming, to SYCL, or anything you want to ask. High-level question or maybe more detailed question. Or if you want, I can show you more advanced stuff. For example, how to create a DAG or to create a functor or this kind of thing. I know it's late in the day, and it was a tough day, a lot of full of C++. So we can do as it is more for you or for the audience. I'm here to help, so as you prefer. Let me read in the meantime when you mind on the question. Oh yeah, if you want, we can talk. If you want, ask us some how can I say, CUDA to SYCL overview, what it is different, what is the same, the terminologies and everything. We can talk about that too. On SYCL interop with MPI. Yes, it is a good question. Yes, so to respond to this particular topic, SYCL interoperability with MPI have nothing to do with SYCL and have everything to do with MPI. I think it is the common approach. If you have an MPI aware implementation, so that means if your MPI can use directly GPU's pointer, GPU's address, you can just do USM SYCL malloc devices, take this pointer, passes to MPI, and MPI will do the thing you want to do to be able to transfer via using NVLink or whatever. So this one is, I think it is the first answer is like it is more MPI job. If you're now asking about buffer, what happens if you are passing buffer to MPI? The answer is it's a good question, and I don't know. I think you can take the raw pointer from the buffer and pass it via MPI aware. Intel have an MPI aware implementation, and this is what I do when I use SYCL. I pass a USM pointer, so I take the raw pointer of the buffer. Or I use USM most of the time, and I use that, and you have all the good things that you use from MPI. But with the buffer, I think MPI need to understand the concept of buffer, and it start being, I don't know. And after, I think it's an expansion to the MPI specification. I don't know. So for the accessor, I can show you that Tristan have a comment that it's true that accessors are only inside the queue submit. It is true and not true. I have an example where there is called, how it's called, placeholder accessor I don't remember the term, but you can create accessor outside of the region, pass them, and after bind them inside your target region. It is possible. I think I have something here. Let's see, I think I do that. Grep, I think it's placeholder. Place. Let me see. No. Well, I don't know what to do. Maybe my functor. Sorry. Stream. No. So here I still generate my accessor inside. Do you remember, Abby, how it's called? The accessor that you can bind later and not directly?
No, I don't remember that.
So yeah, I don't remember it either.
So it exists. I know. But yeah, accessors are only valid inside. Indeed, after they are not valid. But you can create as many accessors as you want. Yeah, exactly. Yeah. So accessors are only. In theory, you can just pass a SYCL buffer and they will do the accessor inside the MPI call. This should work. But now MPI, you need to be able to pass a buffer to MPI who doesn't handle MPI, just like row pointer. And yeah, so this is a good question. I will follow up with my Intel expert here to be able to know what they plan to do. Yeah, so the device memory are not free when the accessor goes out of the scope, is when the buffer is going out of the scope, right? So accessor have nothing to do, at least my understanding is accessor just say how you will want to access data, but this buffer will cause the moving back and synchronization are not really accessor. It is a good question. And let me see, I'm sure I have an example somewhere about this kind of strange. Maybe I don't remember. I guess maybe I dream. If you want, oh yeah, the functor. Somebody asked for a functor. I can show you the functor now. Parallel for functor. So this is, if you want to do that, right? So here I have a queue. Inside my queue, I create a functor, right? And this functor, I pass it to my parallel for. And so here, if you see the signature of this functor, this operator overload of the parentheses text indeed the indexed. And after I can just pass. So this worked. So this is how for the question of functor. And maybe it's DAG Q functor. Accessor. Let's see. Host accessor. No, it's not accessor. I think it's called placeholder accessor or something like that. Sorry, I didn't. I never use these kind of things. But yeah, it exists. So you can create accessor outside and after pass it or something like that. And who generates the accessor? I think is you. It's an accessor that you can generate it outside of anything, and after you can just pass in as an argument. So you don't need to bind the accessor inside the CGH or something like that. I think it is something like that. Oh yeah, exactly. The accessor can be stored across summit boundaries. This is what I tell you. Yeah, it is possible. You can store accessor outside the boundary. It exists. We can talk more later. Sorry, I don't have example. I know it exists. Maybe it will not really fit the use case you want, but it is for sure a possibility. But yeah, don't remember. So this one is more a complete example of a DAG if you want just to be general and queue a lot of kernel. So I got fun with std bind and placeholder and all this kind of thing, where here my kernel I am passing kernel to my q.submit directly. And after it is the kernel who are creating the accessor inside everything. So I have my f copy creates the accessor, and inside this accessor, this function I can use a parallel for, and here a functor. Not sure it is really useful. It was just more that to see, to test this data transfer. Because here, like, I do A to B, B to C, and C to A. So I should see only one data transfer from this guy is on the CPU. I mean, at the beginning is data transfer to the CPU. This one is the GPU data transfer. This one is the GPU data transfer. This one is still a GPU data transfer. And at the end, A are written back to the CPUs. So if the buffer and accessor, the runtime is doing a good thing, I should be able to see only one CPU to GPU data transfer and one GPU to CPU data transfer. So this is a little code I do to benchmark that. And indeed, it is the case. I don't have spurious data transfer, or at least I don't have it anymore. So this was a little fun implementation. Any other question about interop, maybe multi-GPU programming? It have been a rough day with a lot of stuff, so. Maybe the last one, and after we can stop early. We are not paid by the hour. And you can text me, because I think this example is just to show you how to use, you know, what I call you one MPA with the one MKL, sorry, with the MKL for implemented for SYCL. And this one is an example from Intel. I think it was contributed for Intel. So it's just a gem, I think, and you see it's MKL, so you have the same variable, and you have also the generator number. So this one is from the STD, but I know MKL have some too. And after, at some point, I just have, if you are just in the CPU land, you just call cblast gem, and you pass all these good major, row major. And if you are on the GPUs, what you do, you just call one API MKL blast gem, and the only thing would change is the signature of the function. Is here you pass a device queue. So you need to know where you need to submit the kernel, right? In which queue, in which device you need to execute this blast. And like other kernels, this thing return an event, and after you can wait on the event. So we don't support call inside your kernel. You cannot call MKL, right? So inside your parallel 4, you cannot call gem. But what you do is you submit a kernel with call gem. So this is maybe the only limitation. But you see, if not, it's not. You create a buffer and you can pass directly the buffer. Or you can create also a row pointer USM, and you can just pass them, and it will work out of the box. So you see here, Intel does the standard thing of creating the buffer inside the scope. So when you go out of the scope, the buffer are desallocated, and you have a synchronization. That means this device queue does wait is more or less useless, right? It's just to be really sure. And I think that's it. We can stop here if everybody is tired and nobody have a other question. Let me put back my slide to maybe to re-put the conclusion, and maybe more all the reference guide and all the data that you have. So a lot of good resources exist, and I think David say GPU programming, we have a lot of the same kind of philosophy everywhere. So if you learn Cocos, if you learn SYCL, if you learn Regia, at the end, all this, you have a good, it's easy to transfer some information from one from the other. So you may have some subtlety difference between the two, but the core concept of GMU programming, we are extracting the maximum parallelism inside your kernel and outside your kernel, and minimizing as maximum the data transfer. This one are really, really everywhere. You can read the nice reference guide with, you know, this little 1 page, 2 page where a lot of information are inside. So it's really nice to give you a nice example if you don't remember. You have the full specification with honestly not too bad for a specification, far better than the OpenMP specification because it is smaller. A lot of examples. So we have the SYCL trainings that we show. We have a code play who have a fantastic job. We have old Intel Jeff Hammond who have a good DPC purpose tutorial. Know what I go, you can just go on GitHub and type SYCL and you will have a lot of good resources. A lot of video, for example, the video of the SYCL Con are really nice. The code play people did correct. Lot of good tutorial on USM because, you know, USM is complicated with host allocation. Christian talked, for example, about host allocation. SYCL have host allocation too. Host allocation are memory who are on the host, but can be accessible on the device, but will never migrate to the device. So we have that. So a lot of things are here. And maybe for the older people who like books, they are still exist. I am one of them. You can, these books are written by a lot of Intel people. They put DPC++, but it's not really important. It's really more like a good introduction to SYCL that you can read before going to bed during the winter. It's always a good thing. And thank you very much. I think we can finish early. I think everybody will be happy to finish early. So I really like you for your attendance, for all your questions. Don't hesitate really to send me any question on Slack, to send me an email, or I would, particularly if you found a performance bug. I am really interested on performance bug, only on Intel hardware because Aurora will be on Intel. So if SYCL is bad on CUDA, it will be good because we can make a better story for our hardware. I am joking. Performance is important everywhere. And I think it's always good when everything worked. So I think I can stop here if you have any last question. And if not, we can just stop here.